Hello and welcome to ML with AP. We'll continue with our journey on ensemble learning. In first video, we saw the intuition behind bagging, boosting, and stacking. In the last video, we saw what is bagging and a special case of bagging, which was random forest. Today, we'll try to understand what is boosting and in particular, what is adaptive boost or AdaBoost. Let's learn. Friends, boosting is a technique which is again coming from ensemble learning. That means it will be a combination of models, right? Very similar to bagging technique, although it's a combination, but instead of being all these models running in parallel, these are more sequential in nature. They provide feedback from one to another, and I will try to tell you how. Let's try to understand a very simple example of boosting with this diagram. So let's say, again, over here, we have n models which we have created, model 1 to model n. Since this is ensemble, we have created n models. For the example, let's see that all are decision trees over here. The model 1, whatever prediction it will do, okay, now it will do some wrong predictions. That particular wrong prediction will go as a feedback to model 2. Model 2 will pay special attention to those observations which were wrongly classified if it is a classification setting. Model 2 will again pass that particular input to model 3 and subsequently. So model L ultimately, when it will reach to model N, whatever errors, the past errors has happened from model 1 that were corrected in model 2, whatever model 2 did was corrected in model 3. Similarly, model N will become much more mature, robust, and higher predictive power. After that, what we are doing the weights also. So in ensemble, in bagging, if you recall, what we are doing, we are taking the majority vote over there, right? Here, what we are doing, we are taking the weights of the model, okay? So the model also has weights. Now, when it comes to the final prediction, right, what we'll do, we will take the input or the prediction of model 1 multiplied by the weight given to model 1, and we'll see how these things are calculated. Similarly for model 2, and we'll add all of these. So how the equation will look? Equation will look like model 1, its weight, plus model 2, its weight, model 3 plus its weight. So it's taking a weighted average or weighted sum over here to do its final prediction. And this is true both in classification as well as regression settings. Okay, clear? Now, there are a few concepts which we need to know before we deep dive into the boosting techniques. So what are the important points? The first one is it's a generic ensemble algorithm. Like bagging, this is also general. So it can be implemented the base estimator. And what is the base estimator or the base model? These are my base models, model 1, model 2, model 3. These can be anything, SVM, neural network, logistic regression. It doesn't have to be decision tree in particular. But it is usually implemented with decision tree and decision tree stumps in particular. Now we'll come to that. What is decision tree stump? Now decision tree, as you know, right, it's an inverted tree and it can attain number of levels, right? The further you grow the tree, the depth of the tree increases. That the levels of the tree is called the depth of the tree. In this particular case, in case of boosting, we usually limit, if you are using decision tree, we limit ourselves to only one split or two split at the maximum, right? We'll limit ourselves to one or two splits. That is called a stump. So we do not let the tree grow fully. And there is a reason for that. We'll just see that. So there is a concept of weak learner and a strong learner. What is a weak learner? So the concept behind boosting is that all these models, model 1 to model n, they are weak learners. What are weak learners? That they do not have very good predictive power. Their predictive power is only better than a random classifier. A random binary classifier is what? Coin toss. If it is a true false, there is a 50% chance it's true, 50% chance it's false. So weak learner, in case of a binary classifier, you can assume that it is better than a coin toss or better than a totally random classifier. Suppose there are 3 categories to predict. Random classifier will predict these 3 with equal probability, like 33 whole 1 by 3, 33 whole 1 by 3, 33 whole 1 by 3% probability. If my weak learner is predicting better than a random classifier, slightly better than a random classifier, that is a weak learner. Okay, I do not want my individual models to have very good predictive power. That's why I'm not growing the tree to a large depth. I'm restricting my tree to the depth 1 or 2. Why I'm restricting my tree to the depth 1 and 2? Because I only need the stumps. Because I need the weak learners, and the combination or the ensemble of these weak learners will give me a good predictive ensemble. If it's a tree, then ensemble tree boosting algorithm, right? That is the concept behind weak learner. What is a strong learner? The combination of all these turns out to be strong, right? And the details of that lies in the algorithm, which we'll just go through. So this is the concept of weak learner. Slightly better than a random classifier, decision tree stump. Now friends, you know what is decision tree stump? It is the depth of the decision tree is close to 1 or 2. That is called decision tree stump. A strong learner. What is a strong learner? It has good predictive power. The ensemble is a strong learner. Many weak learners combine to make a strong learner. Idea of ensemble weak learners to make a robust, good prediction a strong learner rather than build one single complex model. So ensemble is always a group. So in case of this group, we do not want to create one single complex decision tree with good predictive power. No, we want to make multiple weak learners and have a combination of them, and then that combination should become a strong learner. That is all these models, our boosting techniques or bagging techniques, these are called additive models. Why they are additive in nature? Let's see what we are doing over here. Model 1 is feeding it back to model 2. Model 2 is feeding it back to model 3, right? And what we are doing ultimately, we are taking the weight of model 1. We are taking the weight of model 1, multiplying by model 1 output or classification prediction, and then the sum total of that we are taking as an ensemble, right? So the individual predictions are getting multiplied by a weight, and the combination, the sum of that is being given as a final prediction. That is additive model. Now let's try to understand boosting with one more visual example. Right? I was seeing over here that model 1 is feeding back to model 2. I didn't tell how it is feeding, right? Let's see. So this is my iteration 1. Iteration 1 is nothing but my model 1. Suppose I have a binary classification issue problem, right? So there are plus and minus, 2 classes, right? So my first decision tree or weak learner or a stump of the decision tree, what it is going to do? It is going to do a very basic classification, since it is just only one bifurcation is there, right? Depth is 1. So it will only divide the space into what? 2 parts, right? Yes, no, right? Greater than this, less than this, something like that, right? A decision tree with depth 1 will only be able to divide it into 2 parts, right? So this is what it is doing. It is initially dividing it into 2 parts. Then it notices that, oh, I have done a misclassification. This part, the blue part, is correct. It is all plus signs. On this part, it has done 3 misclassifications. What it will do? It will pass that input back to iteration 2 or model 2. Now, what model 2 will do? Before passing the weights of, there are 2 weights over here, friend. One is the weight of the model itself. Second is the weight of the observation. So the weight of the observation will increase. That's why it is showing you a bigger, the misclassified pluses are showing as bigger. That means the weight has increased for those observations. By weight has increased, I mean that the next time when the subsampling is happening, right, when the samples are being taken, there is more chance of these weights, these observations to be picked in iteration 2 or model 2, right? Because their weight has increased. Their weight has increased, that means in subsampling, there are more chances that it will be picked, right? There is a sampling with replacement, okay? Now, why we are picking more? if we are increasing the weight, if we are increasing the probability of those observations to be picked more often, that means my classifier is going to pay more attention. My model 2 or iteration 2 classifier is going to pay more attention to those misclassified observations, right? So my iteration 2, what it did, it divided it like this, right? It divided it like this. Then it saw that, okay, again 3 mispredictions are there on the negative side. What it will do, it will increase the weight of these 3 mispredictions or misclassifications, right? These 3 minuses, okay? It increased the weight. And then the model 3 was run. And then it, again, because it's a stump, it can only divide into 2 parts. So it divided it like this, okay? So negative, 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 again it divided it like this. Now let's say my iteration, I am only building 3 models. Generally you build 100 and 100, around 100 or even more than that decision stumps, right? And you take the aggregate of that, weighted aggregate of that. But let's say for example sake, we are only building 3. What will happen? The final classifier is an additive sum of these, right? So the weights of this will be defined, and how that weight of this classifier will be proportional to the number of misclassification this classifier has done. Similarly, the weight of this classifier will be the number of misclassification this particular classifier has done. Similarly over here. So what we'll do, we'll do the additive sum, or the sum of this weighted sum. So we'll take this, we'll put it over here, multiplied by some factor or some weight, right? Similarly over here, similarly over here. If you combine all 3, right, one on top of other, you will get this particular diagram. And this particular space, when you see, right, the boundaries, decision boundaries which all 3 combined have done, you can see that it has perfectly classified the negatives and the positive samples, right? So although these were weak classifiers, individually, model 1, model 2 and model 3 are weak classifiers, right? They didn't do very good job at prediction. But when I did an additive or weighted sum of that, the final classifier turned out to be a strong classifier with good predictive power, right? At least on the training data. We can see it on the training data that it is performing very well, right? So this is the intuition behind boosting technique, okay? This is the intuition behind boosting. Let's see. So what are the types of boosting algorithm which are available? There are many actually, but the 3 most popular ones, we are going to only deal with those. So the first one is AdaBoost or adaptive boosting. We are going to learn the algorithm behind adaptive boosting or AdaBoost today. The next one is gradient tree boosting, and a variant of gradient tree boosting, and we'll see that what it is XGBoost or extreme gradient boosting. We'll park gradient tree boosting and XGBoost for next video. Today what we'll see, we'll try to deep dive into adaptive boosting, AdaBoost, and we'll see how to code that using Scikit-learn also. So this is the original paper from 1995. Robert A. Shapiro, he was the one who proposed this algorithm, AdaBoost or adaptive boost. This is the original paper. I have taken a screenshot from there, and we'll try, and here over here he has tried to mention that what the algorithm does, right? It looks very mathematically challenging, but we'll try to break it down and we'll see that what each of the individual terms mean. So here is that AdaBoost algorithm, right? It is very similar to that, not exactly same, but it's very similar to that, right? And we'll try to break it down step by step and see what is it. Okay, let's try to see that what AdaBoost is doing. And this, for this particular example, AdaBoost is both for regression also, but we are seeing it for classification and especially for binary classification. That means my output has only 2 labels, yes, no, true, false, that type of thing, right? So we are taking a more simplistic example to understand the algorithm. Okay, what is the input? The input is saying the data set Z, Z1, Z2, Zn, with Zi being Xi, Yi. Okay, so my data set is nothing but what it is saying is my data set is Xi, Yi. That I have one feature and one output, right? One label assigned to that. Where Xi is what? Xi is some over here it's some number, right? It's some number, and Yi belongs to the set -1 and +1. So for negative class or no class, it it is saying -1. For positive class, it is saying +1. The model will remain the same even if you do 0, 1. It will with a slight tweak. But just to understand, understand that it is predicting negative class as -1. The label will be -1 and the label will be +1 for positive class. Okay. And how many classifiers we are building? How many models or iterations we are going through? M. We are going through M classifiers, right? Now, what is the output? Output will be, I will get a strong classifier H, and this strong classifier is termed as H, and it will predict what values? -1 or +1. It will predict binary classifier, so it should predict either -1 or +1. -1 for negative class, +1 for positive class, right? Clear? Okay. The first step is to initialize the weight. What do you mean by initializing the weight? Now, friends, I was saying over here, right, that each observations over here has a weight associated with weight. When we have to initialize, what should be the probability of getting each of these individual observations to be picked in the sample? Okay, what should be the probability? Let's say we have n observations. N is the number of observations. Okay, so let me just deal with that. So let's say where we have, let's say we have n sets. Okay, n such observation in our bag. Okay, and such observation in our bag. What should be the probability of initially, when you are initializing it, what should be the probability of each of these elements? We do not know whether to assign more weight to this or more weight to this or more weight to this. We do not know. We should assign equal probability to each of these weights. What will be the equal probability? Let's say with an example, there are 8 balls. What is the probability? What will be the probability of one ball to be picked or one sign to be picked, one observation to be picked? 1 by 8, right? Similarly, if there are n observations, what will be the probability of one element or one observation, one row to be picked? 1 by n, right? So this is my initial, without knowing anything in my first, when I'm initializing itself, right? What should be the probability? The probability should be 1 by n probability to be picked. So equal probability I am initializing for every observation to be picked. That's what it is saying, the first line. Okay. Okay. And from where we are picking? We are picking from the set m is equal to 1. What is this? A small n. So I am building what? I am building capital M models. Like capital M time iteration I am doing. And m is equal to 1 is that my first iteration. In my first iteration I am doing a weights. And how I'm assigning a weight? I'm assigning a standard weight like 1 by n, right, to everyone. Clear? Now second, this is a loop which we are doing. The m is my variable, right? The m is the number of models. The capital M is the number of models, total number of models. Let's say it is 50 or something. And m is my variable, something like I from 1 to 50, right? This is what it is doing. So when m is less than equal to m, small m is less than equal to m. So for my small mth iteration, what I am going to do, right? What I am going to do? The third point is saying that run weak learner on Z using weights wi, yielding classifier hm, which will give this. Now let's break this particular thing down. Now friends, every classifier will have an individual weight, right? And every observation will also have an individual weight, right? So this particular weight WIM, this is the weight of the observation. The classifier weight is represented by alpha over here. So alpha m means the mth classifier weight. WIM means the mth classifier ith observation weight. How many total observations we have? We have n observations. So what will be the weight of the ith observation for the mth classifier? Now let's try to understand. Let's say this is my small mth classifier and this is my ith example. What is the weight of this particular plus is I'm trying to refer over there, correct? So W subscript I superscript m means that for my mth observation, mth model, an ith observation, what is the weight of that? Okay. Run weak learner Z using weight, using this weight, yielding classifier this. Okay. So what weight I'm using? I'm using WIM weight, right? Now we'll see how to calculate those weights also, right? But just see that this weight has come from the last model, right? What we'll calculate? The first thing which we are going to calculate in the step 4 is compute error with model M. How we are calculating error with model M? What we are summing? We are summing the weight, the individual weight of the observation. And this particular thing, if you see, let me write it down over here. Okay. So my error M is equal to I is equal to 1 to N WIM H is my model minus YI HM XI. Okay. Now let's see. So this is what is being written. Let's try to break it down, that what it is saying. So it is trying to calculate an error based on what? Based on all the observation. It is summing over I is equal to 1 to N, correct? And this is my weight of the individual observations. So ith observation, mth model has this particular weight. I told you. What is this thing is doing? Now friends, my labels are what? +1 and -1, right? These are my labels, right? So my prediction, this is my prediction. This particular thing is my prediction from that model. This could be either +1 or -1, right? This could again be either +1 or -1, correct? These are the only two observations. These are only two options which can happen, correct? Now let's try to understand. If this is plus and plus, if this value is plus and this value output is also plus, that means they are predicting the same thing. Both my ground truth and my prediction is the same thing. Then this value will be positive. The overall value will be positive, right? Correct? Let me use the different ink. Okay. My overall value will be positive. +1, +1. Similarly, if this was negative class, then this will be -1. This also, if predicting the same negative class, that ground truth and prediction both are same, then -1 and -1. In these two cases, they are same. They are doing the same prediction. -1, -1, +1, +1. So if my ground truth is same as my prediction, that my predictor or my classifier, the mth classifier, is predicting correctly that observation. That's what it means. Then this value will be what? What this value will become? This value will become +1, right? So -1, -1 becomes +1, +1, +1 becomes +1, right? This whole value will become +1, and negative of that will become -1. So this whole thing will become -1, right? If the predictions are correct. So let me write. If prediction correct, right? This value will be -1. If prediction wrong, what will happen in this case? Let's say there is a mismatch. Okay. So there is +1 was the ground truth and prediction was -1. So +1, -1, what will happen? Or similarly, -1, +1. If the predictions are wrong, then this particular value will, what it will become? It will become +1, right? Because this thing will become minus, and minus sign in front of them will make it plus, right? If prediction is wrong, then it will become +1, correct? What will be the effect on error? If suppose we'll come to know how this weight is calculated, but let's say this weight is a positive value, okay? This weight is a positive value. Then positive value into -1 or positive value into +1. If predictions are correct, then my error will be, what will be my error? It is lower down the error because it will become a negative value. If my predictions are correct, my error rate should be low. Correct? Makes sense? If my predictions are wrong, if my predictions are not matching, that ground truth was +1 and I'm predicting -1 or vice versa, if predictions are wrong, then this particular value becomes +1 multiplied by weight, which is a positive number, will become positive. So error will become, overall will go high, what will happen to error m? Error m will go high if my prediction is wrong, right? And error m will go down if my prediction is right. Now friends, think for a moment, does it make sense or not? So the error of the model should go high or low if the prediction is wrong. It should go high if the prediction is wrong, correct? And my error should be low if my predictions are right. If suppose more predictions are right from that classifier, all of the predictions are right, then what? Error should be 0, close to 0, right? If my predictions are more wrong, then I should project a higher error rate, right? This is what it means. Okay, I hope this is understood. So line number 4, if you see this error m, I hope this particular thing is understood. Okay, now let's see line number 5. What is line number 5 saying? Line number 5 is saying alpha m. What was alpha? Alpha was my weight of the model or the iteration or the classifier, individual classifier. Okay, this was my weight. Okay, now what it is written as? Half log, natural log of 1 minus error by m, and this is the weight of the weak learner. So this is the weight. Alpha m is nothing but the weight. Let's try to see that what it means. So this is the formula, right? Now let's see that what will be the weight of the learner. Not the weight of the observation, but weight of the classifier itself, individual model itself. Okay, what will be the weight of this? For now, just let's see the error. Let's say my error m is greater than half, and 2 scenarios. Error m is less than half. Okay, if my error rate is greater than half, what does it mean? That it's a good prediction. It's predicting at least more than a random classifier, right? Correct? It is predicting more than a random classifier. What will happen? Let's try to see it with an example. If error rate is greater than let me take example of 0.8. If error is less than 0.5, let me take an example of 0.2. Okay, these two classes, and we'll try to evaluate this particular thing. Okay, so half log 1 minus 0.8 by 0.8, right? This is the first case, this is the second case. We are dealing with first case. Okay, when the error is 0.8, let's say, what will happen? What will happen over here? If you see half ln, this will become 0.2 by 0.8, which is same as half ln 1 by 4, right? Okay, any log of any number which is less than 1. What is the log of 1? Log of 1 is considered as 0. Anything which is more than 1, the log will become, a log of 2 is what? Is a positive number, right? What is the log of 0.5? It is a negative number, right? So anything less than 0, it becomes negative, correct? This is the property of log. Log of 1 by 4 will be what? It will be a negative number. So again, to repeat, natural log of 1, log of 1 is what? 0. Log of 2 is a positive number. Log of anything less than 1 is what? Negative number. What will be the this particular number? This particular number is going to be a negative number, right? Correct? This particular number will be the negative number. Now see the other case, number 2. What will be the error? Is my less than half, 0.2, like good classification. Error is less than half means what? Good classification, right? It is predicting at least something correctly, lot of things correct. So let's say over here, half ln 1 minus 0.2 by 0.2, right? Which will be same as half ln, this becomes 0.8, this becomes 0.2, which is same as half ln 4. Now what will this number? This number will be greater than 1, so it will be a positive number, right? So ultimately what it is doing, that if my error is less than half, that it is at least predicting more than a random classifier, then assign a positive weight to this. Okay, if my error rate is greater than half, right, like 0.8 or something, if I'm making many more mistakes, right, then penalize it. This weight will be negative, right? And friends, if you recall, if you recall from our initial example, right? Then what we are doing? We are doing the multiplication of the weight into the prediction, right? So if my model, let's say model 2 carries a negative weight over there, then its predictive power is very, very low, right? I'm not considering its predictions into the overall meta prediction, right, over here. But if some model is predicting positive weight, and then that prediction is considered more, right? That's what it means, correct? So that is the intuition behind your number 5, that how the alpha, the weight of the weak learner, is predicted. Okay. Now let's go to point number 6. For each sample I is equal to 1 to n, what is then? We are updating the weight. Here we initialize the weight, and here we assume, but in a for loop or a while loop, we have to update the weight also for the next iteration, right? That was the whole model, right? That we are updating the weights. These weights are higher, right? These weights are higher. So we are updating the weights. How we update the weight? Let's say that for the ith observation, mth model, the weight will be WIM, which is coming from the last side, into e to the power, this is exponential, that means e to the power natural number e, which is Euler's number, e to the power minus alpha m yi hm xi. Now friends, yi hm xi, you can understand that what it is, right? If the predictions are true, it is a positive number. If our predictions are wrong, the product of these two numbers are negative numbers, right? If it's a positive number, let's say, and again, maybe we should go to and understand this in greater detail. Let's see over here. This was the formula, right, which was written. What will be this value? This will be positive for good classification, right? Negative for bad classifications, right? Correct? This will be, and if you multiply it by the alpha and then the negative of this. Now think of what this whole number will become. This whole number will be e to the power minus something. E to the power minus something. Let's say if we are giving a positive number over here, right? A positive number over here. What will be the overall value of e to the power negative, let's say 2, or e to the power negative 3, or e to the power negative 4? It will be a number which is less than 1, right? Because what will be the e? E is 3 point, 2 point something, sorry. It's some natural number, right? Is 2 point something, if I'm correct, 2.67 or something. To the power minus 2, right? That means 1 by 2.67 square. This is what e to the power minus 2. This number has to be less than 1, right? If let's say on the other case, this is a bad prediction, then what will e be? This number will become negative. This negative becomes positive. So e will become a positive number. Okay. Anything e to the power of a positive number, right, of a positive number will become greater than 1, right? So what this whole thing is doing, if you understand, then it is assigning a weight to a model. This is coming from the last model, right? And this is my new model observation weights, right? And this is my old observation weight. It is multiplying it by, it is penalizing everything where, or it is trying to bubble up everything which has the wrong classifications, right? And it is trying to suppress everything which has the right classification. So the weight of the individual, right? The weight of the individual observations, wherever there was a wrong classifications, will go up, right? Why it will go up? This was negative, wrong classification. This whole negative becomes positive number, right? So e to the power positive number. That means it is going up. When there were right predictions, this will become a negative number. So e to the power negative number, right? It is going down, less than 1, right? It is going down. So it is assigning more weight to the misclassifications than to the correct classification. The correct classification, it is lowering down. The wrong classification, it is bubbling up, right? This is what it means, okay? And the 0.7 is nothing but it is renormalizing. Now my weight should be between, like if my weight, if I have to normalize, that means I am putting my weight between 0 to 1, right? So how will I do? What will I do is that I will sum everything up. It is summing everything up and divided by individual observation. So whole weight, the weights of which I am finally passing, SM, is nothing but, SM is the sum of all the weights, right? SM is nothing but sum of all the weights, and I'm dividing individual weight by sum of all the weights. What it is doing? It means that if my weight was 5, let's say 5, 10, 15, 20, 30, right? If I sum them up, let the sum become 100, and then I'm doing 5 by 100, 10 by 100, 15 by 100. What I'm doing? I'm doing normalization, and by that I'm making it and bringing it between 0 and 1. So the sum of all the weights should be 1, right? That's the concept of normalization. Okay, I hope friends you understand that why we are doing this particular 7 steps. I'm adding all the weights, summing all the weights, and I'm dividing by individual weights, so that I'm doing a normalization, right? So my individual weight should not be in greater than 1, right? It should all be constricted within 0 to 1, right? This is what I am doing, number 7. Number 8, what we are doing, again, for iteration, we'll pass on to the next iteration, right? We go from m to m plus 1, right? We are increasing the counter and we are repeating the same thing over here. What will be my final classifier? My final classifier, again, it looks little scary, that sin j is equal to 1 m alpha hji. It is nothing. It's very simple. So what is the sine function? The sine function, my output label first, what it was. Output prediction is that positive class 1, negative class -1. This is what I have to predict. This is what I promised that my classifier will do, right? What it is happening? Alpha j, hj, alpha is the weight, right? The weight of the model. Hj is the prediction. And I'm summing all of them up from j is equal to 1 to m. So all my model weight and their individual prediction. This is what I promised here, right? Over here, all my model weight and their weights, all the model prediction and their weight, and I'm summing them, additive model, right? Remember? I'm summing them up. And what I'm doing after that, this sum is very easy to understand, right? Alpha j, hji. So individual model into their weight, and I'm summing them up. What is I'm doing? Sine. The sine is a function. What it will do is, any positive value, any value greater than 0, you bump it to +1, right? So the output of this particular thing is, let's say, positive, is greater than 0. Then predict +1. So the output of this whole sine function will become +1. If this thing is negative, then output will be -1. This is what it is doing, right? Makes sense? So this is additive. Why it is additive? This is the part where it is getting additive modeling, right? It is getting additive modeling, and it is predicting your negative class or positive class, +1 or -1. So friends, I hope this algorithm and the math behind it is understood by you. If not, let me know in the comment, and probably I will try to answer those questions if you have any doubt over here. Okay? But the funda is very simple. Simple in the sense that each observation has a weight, the first thing. Each model also has a weight. We are building M models, correct? From one model to another model, when we are passing, based on misclassifications, we are increasing the weight of the observations. How we are increasing the weight of the observations? By this particular formula, right? We are increasing the weight. We are increasing the weight of the observation. Intuitively, you understood that why the weight should go up or low or down. If the misclassification is there, those observations which were misclassified should go higher in the weight, right? In the next iteration, in the next model, so that there will be more attention which will be paid over there, correct? Finally, when all the M models are built, what I'm doing an additive model. What it means is that weight of the model, and how the weight of the model is calculated. Weight of the model is calculated by this. This is nothing but, if I have to say again, this we have already understood what is error M, but this is nothing but the rate of misclassification. If you are doing more misclassification in that model, that means that model is not so good, right? Very weak learner. So I will assign a smaller weight to that. If one particular model given more correct predictions, I am assigning higher weight to that. That's what it is doing. And then I am multiplying it by individual prediction by the weight of the model, summing it up, and then passing it through a sign. Why I am passing it through a sign? So my output label should be -1 or +1. That's what I want, right? My output label should always be +1 or -1 for positive and negative samples, right? Correct? I hope, friends, this algorithm is understood, right? Here again, just to reiterate, same example, but in iteration 1, if you see what my decision tree stump has done one decision boundary over here, right? And all the weights are individual. When I pass to the next one, my misclassifications got more weights, right? The size of the circle has increased. That means it has got more weight. Over here, again, I tried to number 3 over here. I did this, right? Yeah, I did this. Again, what were the misclassifications? The misclassifications are this, right? This one, the triangle ones. The triangles got more weights. And finally, if I have to sum them up over here, everything will, the aggregate of that, right, will actually give you a very strong learner, a good prediction. Okay. Now this is another graph which I took from the internet or some paper, but this, what it tells you is, let's try to understand. So if I use a single stump, like one stump of the decision tree, and I pass my classification algorithm through that, that single stump is a weak learner, right? What it will do, what will be my error rate? Error rate of 0.5 is like coin toss, right? Random classifier. This is also binary classification. It is performing slightly better than a random coin toss, right? So it is a weak learner. A single decision tree, only one bifurcation, only one division of the node, right? Root node and one division, that's it. Depth is 1. If suppose I build a decision tree with 400 nodes, what will be my test error? The test error, and this is based on some sample data, sorry. The test error will be over here, right? It has come down to 0.25 or something. From single stump as weak learner, if I do a single decision tree of 400 nodes, it is coming over here. Okay. Now, let's say if I am doing this, and this, what is this red line? The red line is our boosting algorithm, right? Adaptive boosting. So if I do adaptive boosting, on the y-axis, if you see, this is the number of iterations or the number of models I'm building. Suppose I build 50 model, my error is almost close to building as 400 node tree. If I build 100 iterations or 100 models, my error has gone down to 0.2. If I have built 400 decision stumps, right? 400 models or 400 iterations I am doing, then it's almost like 0.1 or something. The error rate has gone down to 0.1. So this kind of gives you an idea that how a weak learner became a strong learner when we combine the power of several weak learners over here, and how one strong learner is still poor than a multi-combination or ensemble of several weak learners, right? Friends, I hope you got those intuitions. Okay. With that being said, let's go and see the code. Okay, friends, this is my Jupyter notebook. Let's play with the AdaBoost. So what I'm doing is I'm importing my libraries, especially AdaBoost classifier, because I'm doing a classification, and through make classification API, I'm generating my samples. What samples I'm generating? 1,000 samples I'm generating, 1,000 observations. How many features? 10 features. Okay, let me run this. So I have generated, my X shape is what? 1,000 observations, 10 features, 1,000 labels which I have generated. I'm initializing my model, AdaBoost classifier over here, okay, and I'm passing it through the cross validation. I wanted to see the 5-fold cross validation over here. What is the score? I will run this. Let it come. Okay, the accuracy is 0.85, 85% average accuracy on my 5-fold cross validation. What were the individual scores of those 5-fold? 87, 86, 86, similar like 79, 87. So the average is 85% I am getting on my cross validation score with my default AdaBoost classifier, right? I have not tweaked any hyperparameter over here. Now let's see. Let's play with the hyperparameters. Okay. So what was the default of what we can do is that how many decision tree or models which you have to build, right? That is a hyperparameter, correct? Let's see. So n estimator over here is 50. So by default, your AdaBoost classifier takes n estimator as 100. Let's play around with that. Let me say 100 estimator instead of 50, which was default. So 50 was over here. I didn't provide anything, that means 50. Over here it is 100. When I'm passing this, what is that? 85.4. My score is 85. Not increase, right? So even if I passed 100, it didn't increase. Let me lower it down and see its impact. I passed 10. Okay, it has come down a bit from 85 to 84. If I passed from 50 to 10, let me pass maybe 5 decision tree stumps only, 84%. Let me pass maybe 2 decision stumps, 84%. It seems the data is very can be separated only on one feature, right? That's what the data is. It looks like. Okay. Now depth of the decision tree is another thing which we can play around with. So we said that we only have to give the decision tree depth as a stump or depth 1, right? But let's see that does it decision tree classifier. Okay, you can provide the number of the depth of the tree also, right? It will be, where is it, max depth, right? It is none. That means if you do not provide, it will grow a fully grown tree. That's what decision tree classifier will do, right? My base estimator. And my AdaBoost classifier, the estimator I am passing as a decision tree classifier. Now friends, why did I define decision tree classifier over here? You have to see this. My AdaBoost classifier, estimator is equal to none. I'm not passing. If I'm not passing a decision tree classifier, AdaBoost, then what will happen? Let's see, estimator. Okay. Over here, base estimator was removed to estimator, that is the name. Okay. What it is saying, if none, then the base estimator is your decision tree classifier. So if I do not provide anything, then automatically AdaBoost classifier will take a decision tree classifier as the base estimator. Here I am providing, and in that it will take as the stump, right? But here I am providing the base estimator. Okay, base estimator as decision tree, and I am specifying the maximum depth should be 10. Let me run that. Accuracy has increased to 90.4%. And if, let's say, my decision tree classifier, I'm building it as a 4, let's say, it has reduced 89%. If I'm building like 2 over here, depth 2, 86%. If I'm building as 1, 85%. So you see that how the impact of the decision tree classifier depth on the overall performance, right? Now friends, if you know that, you'll ask that why we do not specify a fully grown tree, right? One, it will lead to overfitting, right? It may give good result over here, it will not generalize well, right? That is the first problem. The second is the compute. You have to train so many trees, if you are doing 100 iteration, you have to train 100 fully grown trees also. So that's an impact on compute also, both the reasons. Okay, regression is nothing different. It's the same thing. What we are doing over here, exactly same. Apart from this is the AdaBoost classifier, we are using the API AdaBoost regression, and we are passing the same thing. And if you do the same thing, here my scoring is, you can use mean square error. I'm using the mean absolute error, right? So my mean absolute error for this particular data set which we have generated from make regression API, the mean absolute error is this. But again, over here also you can do cross validation, you can do your hyperparameter tuning, and all those things you can do over here. So with that being said, I will close this video over here. This was the video on boosting and AdaBoost in particular. I hope you like it. If you like it, let me know. If you have any question, let me know in the comment and I will try to answer that. Thank you. Bye.